Good morning, afternoon, or evening, wherever you may be located. My name is Ellen Mantis. I am the Director of Science at the Health Effects Institute in Boston. I want to welcome everyone to this webinar on a newly released study from HEI, assessing adverse health effects of long-term exposure to low levels of ambient air pollution, implementation of causal inference methods by Francesca Dominici and colleagues. This study is one in a series of studies that were funded in response to needs of our sponsor community for better information on health effects at low concentrations of air pollution. For those not familiar with HEI, HEI is a nonprofit independent research organization that provides high quality, impartial, and relevant science on the health effects of air pollution. HEI typically receives balanced funding from the U.S. Environmental Protection Agency and the worldwide motor vehicle industry. In the webinar today, you will hear from the investigators, Dr. Dominici and our colleague, Danielle Brown, who will highlight some of the important study findings, and from members of the HEI peer review panel for this study, Dr. Sarah Dar and Jennifer Peel, who will provide some insights, some additional insights on the research. As with all HEI studies, this study underwent an intensive peer review process. The peer review panel prepared a commentary on the study that you can find on our website. I will be co-hosting this webinar with Dr. Sverre Vidal, who is Professor Emeritus in the Department of Environmental and Occupational Health Sciences at the University of Washington School of Public Health. He is a pulmonary physician and an epidemiologist with research interest in the adverse health effects of community air pollution and in occupational lung disease. Dr. Vidal served as the chair of the peer review panel for this study. Please note that this webinar will be recorded. There will be an opportunity to ask a few clarifying questions after the investigator's presentation, and then more time for comments and questions after the review panel provides their input. Audience members will be muted, and we ask that you put your questions in the Q&A box rather than the chat. So please put your questions in the Q&A box. Now, before we hear from the investigators, Dr. Dan Kraus will provide some background on why we want to study the health effects of low levels of air pollution and some information about the other studies in this series. Dr. Kraus is a senior scientist at HEI. He has a background in environmental epidemiology and health geography and worked with the HEI peer review panel to prepare their review of this study and their commentary. Before joining HEI, he led several Canadian studies that looked at health effects at low exposures to fine particulate matter, ozone, and nitrogen dioxide. Dan, the floor is yours.
All right, thanks very much, Ellen. All right, so I'll get us started here and give us a little bit of background about why do we want to study health effects of low levels of air pollution. And I am clicking, but my slides aren't going. There we go. So there are a few reasons why we're interested in this topic. As many people are probably aware, levels of air pollution have been decreasing over the past few decades in North America and Western Europe and other developed regions of the world. In the early 2010s, a handful of studies were published that reported effects on health, including risk of mortality associated with exposures to relatively low concentrations of pollution, including concentrations below current air quality standards and guidelines. And despite some evidence, there remained limited evidence about the shape of exposure response functions or concentration response curves, in particularly at the low ends of these curves. And this is the kind of information that's really important for regulators and policymakers, in particular thinking about at what levels should air quality standards be set. So at the right there, I've just put up an example of an exposure response curve. You're going to see more of these throughout the other presentations. This is from an earlier Canadian study. And essentially what we're seeing here is that across the x-axis, across the bottom, we see estimates of fine particulate matter or levels of fine particulate matter, and then up the y-axis, we see increased risk of mortality. And so, as would be expected, where concentrations are higher, we see higher risk of mortality, but what's especially interesting in this particular example is that in this study, we actually found elevated risks of mortality associated with concentrations well below current air quality standards and well below 10 micrograms per meters cubed. But there still remains uncertainty about that shape at that low end. So in 2020, Jay Chen and Gerhard Hook published a comprehensive review and meta-analysis of studies that had been published looking at long-term exposures to fine particulate matter and risks of cause-specific mortality. And importantly, the results of that study informed the recent WHO air quality guidelines. So I've just reproduced here a table from that where the studies are ordered according to the average concentrations of pollution that were assigned to these populations in these various studies. So perhaps not too surprisingly, the first 5 there that I've highlighted in red are studies that were based in Canada, where the average levels of fine particulate matter were lower than 10 micrograms per meters cubed. Then we have a handful of studies that I've highlighted in blue that were based in the US, where concentrations were closer to 12 micrograms per meters cubed. And then we have highlighted in purple some European studies and other American studies and some studies published elsewhere where the concentrations were notably higher. So this review only considered studies that were published up to 2018. But in the last few years, there have been increasing interest in this topic. So we've seen a handful, more than a handful of studies that have looked specifically at health effects at relatively low and very low concentrations of pollution, including some studies based in areas for which we didn't have any evidence before, such as Australia, New Zealand, other parts of Europe, and ongoing research in Canada. So back in 2014, HEI put out a request for applications for studies to specifically study this topic of health effects at low levels of pollution. And in particular, they were looking for studies that could describe the shape of the exposure response functions like I showed earlier. Ultimately, 3 studies were funded, and just some key characteristics of all 3 studies is they all include very large populations, including millions of people in the US, Canada, and Europe. They used a combination of administrative cohorts and traditional research cohorts. They all developed very high quality exposure models that incorporated satellite-derived observations and ground-based observations of pollutant levels and incorporated other data sets. And they all developed novel statistical approaches. So the 3 studies, I'm just showing roughly their geographic locations here. So the first study was led by Dr. Mike Brower at University of British Columbia in Canada. It was a European study led by Bert Brunerkrief at Utrecht University in the Netherlands, and then an American study led by Francesca Dominici at Harvard that we're going to hear more about today. So I just wanted to put this slide up to highlight the teams and acknowledge the PIs and their large teams. Each team has people different expertise related to exposure assessment, epidemiology, statistics, and based at a variety of institutions. So for those of you who aren't too familiar with HEI, we do detailed study oversight and review of all of our funded studies. So in the case of these 3 low exposure studies, we actually convened a special oversight committee of experts to oversee the work by these teams and to make sure that they were staying on task and meeting their deadlines. And the teams had to submit progress reports twice a year. They had to give presentations at our annual conferences. We also hired an independent third party to perform quality assessment, quality control of the data sets that they were using. And then following the completion of the studies, we convened a separate review panel of experts to review the results, review the final reports as prepared by each team. And so a key activity of the review panel is to write a commentary on the reports. And so these commentaries are meant to highlight really the key findings, the key meanings of the results, and the implications of the results, and to put the findings in context with what we already know about this topic. And also, to some extent, to indicate some of the shortcomings of these studies. So as I said, the commentaries are published alongside the reports. These are all available on our website, and I encourage people to look at these. The European study by Bert Brunekreef was published in September, and the Canadian study led by Mike Brower will be published in the spring. And Francesca's study was published last month. Just one other note on this is that there is some ongoing joint analyses that's ongoing among the three teams. So before we hear about Dr. Dominici's study today, I just wanted to say a little bit about Dr. Brunekreef's study that was published recently. This is a really impressive undertaking. It was a massive amount of work. Their team, they developed exposure models at a spatial resolution of 1 kilometer by 1 kilometer for all of Europe for fine particulate matter, black carbon, nitrogen dioxide, and ozone. They used data from 11 countries to do 2 series of parallel analyses. One of these was on a pooled cohort of 15 well-characterized research cohorts, and then separate analyses on 7 national level administrative cohorts. And so in both of these series of analyses, they reported significant associations between cause-specific mortality and long-term exposures to fine particulate matter, black carbon, and nitrogen dioxide. And then especially interesting in this context of looking at low levels of pollution is that they found increased risks for natural cause mortality, even the lowest observed concentrations for fine particulate matter, black carbon, and nitrogen dioxide. So this report is available on our website, and I encourage people to check it out. So for today, as I mentioned, this study was published last month. This is also a very impressive undertaking. As you'll hear, they used a massive cohort of 68.5 million Americans. They developed annual exposure models for fine particulate matter, nitrogen dioxide, and ozone. And one aspect of the study that's really interesting is they considered 5 different analytical approaches for looking at links between exposure and risk of mortality. And 3 of these were new causal inference approaches, and then 2 of these were more traditional regression approaches. So with that, I will thank you and hand on to our next speaker.
Yes, hello, this is Sverre Vidal. I'm going to introduce the speakers for the from Harvard who are describing the study they performed. There are 2 speakers, as you heard before. The first is Francesca Dominici. She's the director of the Harvard Data Science Initiative at Harvard and the Clarence James Gamble Professor of Biostatistics, Population, and Data Science at the Harvard T.H. Chan School of Public Health. She leads an interdisciplinary group of scientists with the ultimate goal of addressing important questions in environmental health science, climate change, and health policy. The second presenter will be Dr. Danielle Brown. She's a senior research scientist in biostatistics department at the Harvard T.H. Chan School of Public Health and the Department of Data Science at the Dana-Farber Cancer Institute. The research interests include causal inference, which you'll hear about, measurement error, environmental health, risk prediction, survival analysis, and comparative effectiveness research. Dr. Dominici.
Thank you, Sverre, for the lovely introduction. And before starting, I really wanted to thank the HEI staff, the HEI Research Committee, the HEI Review Committee, also really to emphasize that this has been work of many people that have providing extremely valuable input. Also, I'm very grateful to HEI for funding additional analysis as we have been learning and improving our work, interacting with my 2 colleagues, Bert Brunekreef and Michael Brower. Also, I wanted to thank Antonella Zanobetti, who is the co-investigator on this project. And as you will see also, Danielle, at the end of the presentation, we acknowledge the many people that are involved. All of this to say that I feel that, this is a work of many, many people that have been contributing enormously to this study. So I will provide an overview of the project on low-level air pollution exposure and risk of mortality in older American. Also, my colleague Danielle Brown, who will provide the second part of the presentation, will be moving the slide, kindly helping me. Next slide, please. Thank you, Danielle. So let's start with the overall goals. So this was a very ambitious project. We wanted to advance in 4 critical areas. One is to predict the short to long-term exposure to ambient fine particulate matter, nitrogen dioxide, and ozone at the high spatial resolution, up to 1 kilometer grid for all the continental United States during the period 2000 to 2016, and linking this prediction to health data. We wanted to develop new causal inference methods for estimating the exposure response curve and adjusting for measured confounders. We wanted to apply these methods to both the Medicare and Medicaid enrollees to estimate health effects that are associated with short and long-term exposure to low level of ambient air pollution. And very importantly, we wanted to really think it through and develop innovative pipelines for reproducible research. Next slide, please. So the research data platform was really, and it is, and it will be, continue to be really an enormous task, and something that was, I would say, a monumental effort from many, many people, because when you're doing a study of this type and that is not designed to be that way, and it comes from getting data stream from heterogeneous data sources, there is a tremendous amount of thinking and work in integrating this data stream from different government databases. So just in a very, very high level, we had a phase that we call a data acquisition, where we gather data from publicly available and government data sources. Then we had in like a task, which is about the alignment, harmonization, linkage, and integration of all of these heterogeneous data to provide estimates of the exposure, to clean and provide an open longitudinal cohort of health outcome, and as well as additional information on confounders. And then actually I would say probably the analysis part is maybe the easiest part, because then at that point we are positioned to develop a new methodology and analyze data, both using traditional approaches, but also thinking about innovative approaches, and try to potentially address, to the degree as possible, question inherent to causality from analysis of observational data, analysis of observational data. We have a GitHub site where you can see, and where it's documented all of the public, where you can access all of the publicly available data sources, how we get an access to the Medicare data, how the code that will provide the linkage of the different database, and then the code that we have used and developed to do the statistical analysis. Next slide, please. So one of the monumental tasks and one of the goals was to estimate exposure to fine particulate matter, ozone, and NO2 at 1 kilometer grid for all the continental United States at the daily level for the period 2000 to 2016. This was an effort that was led by my colleague, George Wars, a professor in environmental epidemiology at Albert T.H. School of Public Health. This has been really something that has been one signature of his research. Him and his colleague and his postdoctoral fellow and student have been developing machine learning model. And the general idea is basically to gather information from satellite that provide imprecise measure of air pollution called aerosol optical depth. It takes output of atmospheric chemistry model. It takes weather information, land use information, train the machine, also, of course, on monitoring data, and then is able to estimate exposure to fine particulate matter for all the continental United States, so not only for PM 2.5, but also for NO2 and ozone. As you can see in the slide, these are the citation of his work, and very importantly, and we should give credit to him and his team here, they've been making the exposure data publicly available for all of the other investigators to use in their own studies. Next slide, please. So these are the estimates, basically the maps that shows the levels of fine particulate matter, ozone and fine particulate matter, NO2 and ozone in both the year 2000 and in 2016 for all of the continental United States. And again, here is the link where you can download this information. Next slide, please. So as I mentioned, data sources, it's something that was really important to take to gather reliable data sources. This is a list. Again, you can find detailed information in the GitHub site about the different government databases that have from which we have gathered all of the different data. With respect to the Medicare data, it's important to clarify that these are data that everyone can access. They cannot access it through us. They have to access it through Center of Medicare and Medicaid Services by setting a data user agreement with ResDoc, and also there will be a payment to buy this file. Next slide, please. Very important to adjust for confounding. We consider it, so the Medicare claims have a limited amount of individual level confounders. So they have age, gender, race, and dual eligibility to Medicare and Medicaid. We substantially augmented with respect to many socioeconomic variables coming from the 2000 to 2010 census at the zip code level. We are augmented with several variables at the county level, and as well as with zip code level variable with respect to weather information that was further aggregated from grid level to zip code level. Next slide, please. So the health data is really what was really, made the entire study possible. And by purchasing claims data regularly over the last now 20 years, we will be able to build we call it the dynamic cohort of 68 million Medicare enrollee. We said that it's a dynamic cohort because every year as a new group of individuals in the United States become eligible to Medicare, they automatically enter into this cohort. So this is a really actually nice feature because this is a cohort that never dies in terms of that every year new 65 years old, newbie young 65 years old enter into the cohort, and so therefore this way we call it open and to new enrollment every year. We have date of death and for all cause, and then we have a date of hospitalization by ICD-9 code. As I said, we have individual level data from based on, and also individual level information of date of death, age of entry, year of entry, sex, race, whether eligible for Medicaid, and a proxy that is for socioeconomic status and zip code of residence. This is something I'm not going to be able to talk about much in this talk, but I also want to mention that in other additional analysis, we also have access to the Medicare current beneficiary survey, which is a random subset, a nationally represented subset of the Medicare population, from which they have phone survey and for which we were able to collect information on an additional more than 120 individual level confounders, including smoking, comorbidity, and frailty. Next slide, please. So, as I mentioned, a big task was the harmonization and integration of these heterogeneous data sources, which lead to, in addition of like a lot of work, also I think an hybrid study design that we need to acknowledge. So we have health data available in the individual level. The exposure is assigned the zip code level, because although the health data is available at individual level, we only know the place of residence of each Medicare enrollee up to a zip code. So we assign their exposure to a zip code. In other words, you can think about that all of the Medicare enrollee, they're living within the same zip code, they have the same exposure. So we assign the exposure at zip code level. We have additional confounder, both individual level confounder, area level confounder. The area level confounder are both at the zip code level and also at the area level. Because we have almost coverage the entire United States, so we are covering approximately 31,000 zip code. Next slide, please. The first landmark publication on this study was a New England Journal of Medicine paper published in June 2017. One of the lead author, Chandy, he was at that time a PhD student, Department of Environmental Health. There we conducted an individual level regression and fitted the Cox proportional hazard model. This study was restricted up to data up to 2012. And this was the first time that really we were able to estimate exposure, the mortality risk associated with long-term exposure to fine particulate matter, also level below 12 microgram per cubic meter. As you can see from this table and focusing on the last column, we have over 32 million individuals that were exposed at the level of fine particulate matter below 12 microgram per cubic meter. Next slide, please. So one of the first findings of this study, so basically what this plot shows is that horizontal line is centered, is placed at 7.3% mortality increase associated with a 10 units increase in long-term average of PM 2.5. We also conducted stratified analysis for different subgroups, for male and female, for different racial groups, and also for people eligible and non-eligible for Medicaid. We did find a much higher mortality risk associated with PM 2.5 for Afro-American population. Next slide, please. So as part of the HEI, then one of the goals that we had was, as we published the New England Journal of Medicine study in 2017, we want to achieve two different additional tasks. One is that we want to extend the study period up to 2016, and more importantly, to really assess the how robust were the results to different specification of statistical modeling, and especially to also reanalyze the entire database, not only with the traditional approaches, but also with methods for causal inference. And here I should really acknowledge that this was really work led by Zhao Hu, who was a former PhD student of mine, and now a postdoctoral fellow in data science at Stanford, and Danielle Brown, which is a senior research scientist, and that she will be speaking in a few minutes. Next slide, please. So here is really the core of our statistical analysis. So as I mentioned in this new publication, the World Adult publication, we reanalyze the whole database, not only using two traditional approaches. So we use the same Cox proportional hazard model that we use in the New England Journal of Medicine. Then we found out that there is an equivalence between a Cox modeling and a Poisson model. You can collapse individual level data within specific strata and then be able to approximate a Cox regression using a Poisson regression, which again buys you a tremendous amount of computational efficiency. And then we have three methods for causal inference. We have a method that we called exact matching, which was a newly developed method. Then we have a weighting approach, which is an existing and well-validated approach in causal inference, and then an adjustment that is also very well validated approach, where matching, weighting, and adjustment were all based on the generalized propensity score, which I'm going to tell you more in a second. And then we evaluate a 95% confidence interval by using Bootstrap. Next slide, please. So this is probably the most technical slide that I'm going to have, but I wanted to at least spend one slide to tell you a little bit about the statistical modeling. So one of the ideas is first you estimate the generalized propensity score, which is basically estimating the conditional density of the exposure, for example, of PM2.5, conditional to all of the potential covariates. You wanted to estimate this generalized propensity score in as much as flexible as you can. We have plenty of data to identify the very rich models. So we use machine learning models, and particularly gradient boosting machine. And then we include that into the generalized propensity score model, both county level variable, census code variable with respect to socioeconomic status, and then meteorological variable. So now we have this generalized propensity score, and so we can either match or weight or adjust by propensity score, and then we consider an outcome analysis, which is basically Poisson regression, but instead of adjusting for confounding factor using linear term, as is always and traditionally done in regression, we are going to adjust for confounding factor using a generalized propensity score, and so therefore we'll be able to adjust for confounding in a much more flexible way. Next slide, please. So why using causal inference method, right? And by no means we're going to be able to tell you all of that in a few minutes. But one thing I wanted, there's a couple of things I wanted to communicate. What are the advantages of using causal inference? Well, I think that one of the advantages is basically that we can quantify and visualize how close we are being able to approximate our observational study into a randomized experiment. So it's give you a sense of how far are we to be really into randomized world. And that's, I think it's a really important diagnostic. So we can visualize, and I'm going to show it to you in a second, whether or not the measured confounders are balanced across a different level of exposure. We also have a very well validated approach and very peer-reviewed in the literature by our colleagues of how we can assess for a measured confounding bias. So by being able to use method for causal inference, whether it's existing method or new methods, we can, we can say a little bit, we can assess how confident we are under a certain assumption of whether or not we can make statement about causality. Next slide, please. So I'm going to go this very quickly. This is the cohort the description for the Hu et al. Paper. This paper is publicly available. It's published in Science Advance. But basically, we now have, as I said, 68 million and over 38 million of individuals that are exposed at a level of fine particulate matter below 12. And so specifically to estimate the effect of PM2.5 at below the level, as low level, we have 259 million person years. Next slide, please. So this is the covariate balance plot that I want to show you and why I think it's valuable for causal inference and why the method for causal inference are valuable. So let me just quickly tell you what this is about. So if you just focus for a moment on the plot on the left, this is just doing a causal inference studies for PM2.5 varying at all levels. The plot on the right is just for doing a study for people that are exposed at level below 25. So the red dots are the correlation between the exposure, PM2.5, and each of the potential measured confounders. And you can see that for some of these measured confounders, so this correlation can be pretty high. So what it means is that if we have an observational study where to begin with, you have high correlation between some of the confounders and PM2.5, it means that you could potentially have confounding bias, right? Now, if you focus for a moment only on the green dots, the green dots are the correlation between H-measure confounders and PM2.5 after we have created, basically, we have reshuffled our observation so that each subject is matched to another subject that has a very close generalized propensity score. So what does it mean is that if you take two people that have very similar generalized propensity score and you match them to one another, you're basically breaking the correlation between each of the measured confounders and PM2.5. And you can see that all of these green dots are below a line centered 0.1. So basically saying that if you calculate the GPS, the generalized propensity score, and you are matching by the generalized propensity score, you're creating another pseudo data set that try to resemble a randomized experiment. Why try to resemble a randomized experiment? Because you are breaking the correlation between each of the potential confounders and the exposure. If you break that correlation, you have less, your threat of measured confounding bias is much lower. Next slide, please. So basically what we found is that if we take the data for the whole range of exposure of PM2.5, you can see that whether we use a Cox or proportional hazard model, a Poisson model, or we use any of the causal inference method, actually in this context, the results were very similar. Now, if we do an analysis where we only restrict to people exposed to PM2.5 below 12 microgram per cubic meter, we see that under the causal inference method, these effects are a little lower than under the traditional method. However, the risk estimates for people that are exposed at low level of PM2.5 tends to be higher than when you're looking at the whole range. So based on these models, we found that lowering the air quality standard to 10 microgram per cubic meter would save 143,000 lives in 1 decade. Next slide, please. So I wanted to turn now on this slide, and I want to turn it to my colleague, Danielle Brown.
Thank you. Thanks, Francesca. So I'll start by talking about the strengths of the causal inference method. So as Francesca just pointed out, one advantage is that we can separate the design stage from the outcome analysis. And so that allows us really to mimic a randomized experiment under a set of explicit identification assumptions. So this really increases the objectiveness of the causal analysis. The other advantage is that it can help guide researchers to actually explicitly state the assumptions, and then allows us to use sensitivity tools like the one that Francesca just described in terms of assessing covariate balance. Also, we can assess the sensitivity to unmeasured confounding using the e-value, and it really allows us to do these assessments. And these models and this kind of framework is actually more robust to outcome model misspecification. So essentially, as Francesca just pointed out, we adjust for confounding through the generalized propensity score model, and then we match or weigh or adjust using that generalized propensity score model. In the outcome analysis, that allows us actually to not need to include the confounders as linear terms in the outcome model, which can be prone to model misspecification. So these are kind of the strengths. There are limitations to a causal inference framework. So some of these limitations that we often require increased computational resources. So we're fortunate enough, we actually use 2 different computing clusters at Harvard that kind of helps us overcome these computational constraints. Some of the methods require a steep learning curve for new researchers, but I think the field of biostat and epi is changing a bit. So I think more and more researchers will become more familiar with these methods, I think, in the future. The methods based on generalized propensity score, they're still affected by unmeasured confounding bias. So if we have unmeasured confounders, we can't include them in the generalized propensity score. That can be a problem. And then the propagation of the exposure error into the health analysis under a causal inference framework is quite challenging. And Xiao and I both have some work in this field, but essentially the error and the exposure needs to be propagated because it affects both the generalized propensity score estimation as well as matching, because we actually match by both the generalized propensity score and the exposure values. If the exposure values are error prone, so will the matching procedure, and then the outcome analysis. So there are a lot of things to think about in terms of measurement error, and I'll talk about it a little bit more later on in this presentation. So I'm going to shift gear and I'm going to focus on the second half of our presentation today, which is on estimating nonlinear exposure response functions. So we actually applied the proposed generalized propensity score matching method to estimate the effect of long-term exposure to 3 pollutants. So PM2.5, NO2, and ozone, and the effects on all-cause mortality. We actually estimate the curves. So we use kernel smoothing approach, which is a non-parametric approach to estimate these curves. We define a baseline rate at the estimated as the estimated hazard rate that corresponds to an exposure level that's the first percentile of the distribution of each of the 3 pollutants. To avoid extrapolation of the support boundaries, we exclude the first and the lowest and the highest 1 percentile of the data when we plot these curves. And then we still evaluate the 95% confidence intervals, like Francesca mentioned, with the M out of N subsampling block bootstraps, and that helps us account for actually the spatial correlation. So I'm going to show 2 plots for each of the pollutants. One plot is going to be multiple pollutant models where we adjust for the 2 other pollutants as potential confounders. And the way we do is we actually include them as terms in the generalized propensity score model. And so that allows us to flexibly adjust for them in the model. So they don't actually need to be specified in the outcome analysis. They're specified in the generalized propensity score model. And then the second plot is a single pollutant model, which doesn't adjust for the 2 pollutants, but still does adjust for all the 14 zip code and county level time varying potential confounders. So I'm going to start by showing the results for PM2.5. On the left, we see the multiple pollutant models adjusting for the other 2 pollutants as potential confounders, again, in the generalized propensity score model. On the right, we see the single pollutant models without adjusting for the other pollutants. We see here evidence of a harmful causal relationship between mortality and long-term PM2.5. We see here, this is the hazard ratio of 1. We do see here a kind of linear increase, and we do see this even at the low exposure levels. So we definitely see aggravated harmful effects at exposure levels, even below the national standards. For NO2, we see harmful impact of long-term exposure to NO2 on mortality. Again, on the left here, we adjust for the 2 other pollutants. So in this case, it's PM2.5 and ozone. On the right, it's without adjusting for PM2.5 and ozone. Something to note is that within the low range, we see more of a flattening of this curve, and more, whereas as you go into the higher range, you do see this linear increase. And then lastly, the figures for ozone. So again, on the left is the effects of ozone adjusted for NO2 and PM2.5 in the generalized propensity score model. On the right is without this adjustment. And we do see here that we see no statistically significant significant effects in kind of the low range, all the way up to even 45 or 50 parts per billion. And then you do see this increase in the very high ranges in terms of the effects. So we also, so these were assuming nonlinear exposure response functions, but we also assumed a constant hazard ratio, and we compared 2 approaches of modeling actually. So the first is the generalized propensity score matching, where we match and then we fit a Poisson model on the matched data set to estimate the constant hazard ratio. So that's this column. And then we also fit a Poisson model where we include all the confounders as actually terms in the outcome model. So not using generalized propensity score methods at all. So we did this for the 3 pollutants. And again, we compared the adjustment for the other 2 pollutants compared to the unadjusted results. So we see here, for example, for PM2.5, we see slightly higher effects unadjusted for the other two pollutants, but still statistically significant effects even when you adjust for the two pollutants at a hazard ratio of 1.036. The Poisson model has a slightly higher hazard ratio. And again, when you adjust for, we also did this adjusting only for NO2, and you still see a statistically significant effect. For NO2, we don't see statistically significant effects for the generalized propensity score matching, and we see very close estimates when we adjust and we don't adjust for the other two pollutants. And then we see a slightly statistically significant effects for the Poisson model. And for ozone, we don't see statistically significant effects here across the different models, and both when we adjust for the other two pollutants and the unadjusted pollutants. So just to kind of summarize the multi-pollutant analysis results. So overall, adjusting for the other two pollutants, we see slightly attenuated causal effects for PM2.5. These are still statistically significant, slightly elevated causal effects for NO2, and the results remain unchanged for ozone. So something that Francesca also mentioned in her first slide and was very important for us throughout this study was to make sure that we're also producing pipelines for reproducible research. So as Francesca mentioned, the study relied only on publicly available data. This is privacy. The health data is privacy protected, but it is publicly available, and you can purchase it with your own data user agreement from ResDec. The Medicare mortality data includes almost 97% of the US population older than 65 over the years of 2000 to 2016. We did spend quite a bit of effort making both the software code and workflows open in GitHub digital repositories. So this is kind of a link to our publicly available GitHub. And in addition, we spent quite a bit of effort developing statistical software to go along with our work. And this is actually one package that we developed is called Causal GPS. It actually contains the GPS matching work and all the algorithm to implement GPS matching. It's available on CRAN. It's an R package. We've had, as of yesterday, over 2,900 downloads, and you're welcome to download it yourself and implement and use it in your own studies. We did also spend quite a bit of effort actually optimizing the algorithms behind the Causal GPS and make sure that they're scalable for large data sets. So overall, the study strengths are that this is a massive and representative study population in the United States. We've done numerous sensitivity analysis, and across the board, the results are quite robust. We have a transparent assessment of covariate balance, as Francesca showed, so that helps indicate the quality of the causal inference analysis for recovering the randomized experiments. The work relies on publicly available. There's code, so you could reproduce it yourself. And conditional on the required assumptions for causal inference, really collectively, all of these results indicate that the long-term PM2.5 exposure is likely to be causally related to mortality. So like any study, we have a lot of assumptions that go into this work. And so I'll step actually through all 5 of these just to make some comments on on the assumptions and the sensitivity analysis that we did to analyze these assumptions. So the first one is the no unmeasured confounding. So we do account for individual and area level potential confounders. The Medicare data has limited information on individual level variables. We do, to mitigate unmeasured confounding bias, we do assess the sensitivity by including year as a surrogate for some of the unmeasured confounders that might have covaried over time. We saw that the results are robust to this inclusion, and so that was a good sign. We also conducted further sensitivity analysis to unmeasured confounding by calculating the e-value, and again, we showed that the results are robust to unmeasured confounding bias. In terms of model misspecification, so the causal inference approaches do require the estimation of the generalized propensity score model. Assuming that all the causal inference assumptions hold, these approaches tend to be more robust to outcome model misspecification because Again, once you adjust for the confounding through the generalized propensity score model, you don't need to include the covariates again in your outcome model. And they do allow for the transparent evaluation of covariate balance, like we mentioned. It's important to note that also if your traditional approaches, if they're correctly specified, will also have the potential to inform causal relationships as well. It's just that some of these causal inference approaches tend to be a little bit more robust to the model misspecification. In terms of measurement error, so the air pollution exposures are estimated using the prediction models developed by Joel Schwartz, as Francesca mentioned. So these models actually perform quite well, but like any model, they're not perfect. So the D et al. Has excellent model performance with a 10-fold cross-validated R-squared of 0.89 for annual PM2.5 predictions. And we did, even with such a high R-square, we did assess the robustness of the results to kind of the exposure model. And what we did is we actually ran in the D et al. New England Journal's Medicine paper, we actually ran an additional analysis where we subsetted the cohort to individuals that are located near EPA monitors. So there's 1,928 EPA monitors that were used. And so if you used monitor predictions for these individuals, the hazard ratio was only slightly lower than the one obtained using the exposure prediction model. So this was a hazard ratio that was obtained of 1.061 compared to 1.073 using the exposure prediction. So again, the results are robust to kind of the way of exposure assessment, whether it's through these EPA monitors or it's through the prediction models. So measurement error, how to propagate them into causal inference. I kind of mentioned this, but it's a tricky and it's an area of active research. We did propose a regression calibration approach for the generalized propensity score framework under categorical exposure. We applied this to assess the association between long-term PM2.5 exposure and mortality in northeastern US, and we have a publication on this. When we account for exposure error, actually the results were, the hazard ratios were slightly higher and still statistically significant association with larger confidence intervals because we were able to really capture the uncertainty and propagate it through the entire analysis. We're working on extending this to the continuous setting, and we have 2 papers on arXiv that are actually under review, both looking at ways to, the first one is looking at ways to really, again, extend this to continuous error setting, and the second one is propagating the uncertainty using Bayesian modeling. Measurement error is not only an issue in the exposure estimates, it's also an issue in the confounders, and that's really also subject to future work, including both measurement error in the confounders and the exposures can be quite complex. So in terms of spatial correlation, so the model parameterization assumes that the zip code information is spatially independent given the covariates. We did adjust for quite a bit of zip code level predictors for mortality, including the socioeconomic status and weather variables. So we do think that this assumption likely holds. There may be some residual spatial dependence remaining, but we do bootstrap, and the way that we bootstrap allows us to kind of partially account for the spatial correlation. So we randomly sample zip codes for the bootstrap, and so we break down some of that spatial dependence given the covariates. So we do think that it's unlikely that our results are heavily impacted by the spatial correlation. We also, just to be even more certain, we actually adjust for potential spatial confounding by including a region as a dummy variable in the analysis as well. And then lastly, like our model is based on a hybrid study design. So Medicare claims like there's very limited individual level data in the claims data. We have information on age, sex, race, and Medicaid eligibility, which is again is a proxy for low income. To increase confidence in our results, and Francesca mentioned this, but there is the Medicare current beneficiary survey, which is a survey on about 8,000 individuals. It includes more detailed individual level characteristics for these individuals. Over 100 potential measured confounders are reported in these surveys. And we do have a study that actually shows that the estimated hazard ratios remain unchanged when you include all these additional individual level behavioral risk factors. So just to conclude, our work really provides a comprehensive evidence on the association between exposure to PM 2.5, NO2, and ozone and various health outcomes. We observe a causal link between long-term exposure to PM and mortality, even at PM 2.5 levels below 12 micrograms per meter cube. And we've shown that in the Wu et al. Study and the Di et al. Study. The work relies on newly developed causal inference methods for continuous exposures. And again, we're constantly working on also developing the statistical software to go along with these newly developed causal inference methods. So feel free to go to CRAN and download our statistical R package. In the multi-pollutant analysis, we see that adjusting for the other two pollutants slightly attenuated the causal effects for PM, slightly elevated the causal effects for NO2, and the results for ozone remained almost unchanged. And lastly, just to reemphasize, our studies are based on publicly available data source. We've made all the code publicly available, and this really maximizes reproducibility and transparency. So yeah, this work couldn't have been done without all of our team members. And it's really a multidisciplinary collaboration across different departments, both at Harvard University and Columbia University. We do also partner with the Faculty of Arts and Science and their research computing team at Harvard. And we have Naeem, who's a software engineer, really leading all of our software work in this space. And just to acknowledge, so we'd really like to thank the Health Effects Institute for their support of this work. We also are really fortunate to have access to 2 computing clusters at Harvard, one run by the Faculty of Arts and Sciences and Research Computing Group, and the second that's supported by the Institute of Quantitative Social Sciences. And we really thank them for all of their support with this work. And so in just a list of references, and I'll open it up to clarifying questions.
Thank you, Dr. Braun and Dr. Dominici. We have set aside about 10 minutes for specifically clarifying questions, and we have a few questions in the queue at the moment, and I'll kick that off with a very basic fundamental question, just for which is critical to understanding, the work that's presented, which is a question from Margaret Gordon, which is basically, what is a response curve?
So what's a great question. So first of all, one of the reasons why it's a great question is that one part of the work that we are doing is actually to try to reconcile the different definition of an exposure response curve, because actually, believe it or not, even among experts today, when they talk about exposure response curve, sometimes they talk about something different. But thank you, Danielle. I think that in our context, the exposure response curve is basically our ability to illustrate how the odds ratio, and so how the percentage increase in mortality vary continuously as you compare different level of PM 2.5. So in the context of a binary exposure, we generally will say, what will be the additional percentage of people that will have a risk of death when they have a high exposure versus a low exposure. In the context of an exposure response function, and continuously, you can basically trace and look at how your risk of death can continuously increase as the level of PM 2.5 increase. And these two figures, I think if you just focus on the one on the right, I think that there are a couple of features to consider. One is that it's almost linear. So that means that for every time we have a change in PM 2.5, you have a percentage increase in mortality. But also very importantly is that there is no evidence of a threshold. So it doesn't flatten up below a certain level of PM 2.5. So what this is recommending, what this is suggesting is that any reduction in level of PM 2.5 independently where you are in the range of the exposure will lead to a mortality benefit by having a associated reduction in mortality risk.
So for another clarifying question for Dr. Brown, were you referring to mixture effect models as multi-pollutant models?
Yes, in the multi-pollutant models, I was referring to these models on the left here, where we adjust for the two other pollutants by including them as potential confounders in the generalized propensity score model.
Thank you. There was a question about the propensity score from Jiajun Luo, who was questioning a question about the continuous exposure issue. I guess the issue about the generalized propensity score, and basically, could you explain more about the continuous exposure using the matching method?
Yeah, and that's a great question. And we developed this approach. So you're right. Traditionally, matching is used for binary exposures, and actually Xiaowu has led the work to extend matching into a continuous framework. And we're actually matching by both this generalized propensity score model that I can pull back the slide, but as Francesca mentioned, is this conditional model of the continuous exposure on all these potential confounders. So we're matching both on the generalized propensity score and on the exposure. So we're actually matching both on both quantities kind of simultaneously. And the paper with the technical details of this work is under review right now. It's also available on arXiv. The link is in the references on the last slide. And it's also quite well, I think, explained in the documentation for the Causal GPS package. So please feel free to download it. And we're very much open to feedback and comments and et cetera. But I think that would be a good resource to look at.
Thanks. There's a comment and question from Tim Wallington. It says that I'm getting a block here. As I understand it, the potential confounding factors of noise and access to green space were not considered in the analyses. Can you comment on whether these might be important confounders?
Yeah, thank you very much. This is a really very important question. So the quick answer to your question is no. In our current, in the work that we have presented and we have that is part of the HEI report, we did not adjust for green space. However, clearly this is an ongoing, we are continuing to do additional analysis. There is a postdoctoral fellow in the team, Johan Klombecker. He's actually focusing on including green space in the analysis. So we have looked at whether green space is an effect modifier, and we will be planning to conduct additional analysis to also adjust for green space. Just in terms, though, of some high-level, preliminary analysis, we don't see that there is a strong correlation between PM 2.5 and greenness. The correlation tends to be pretty low for PM 2.5, but it's a little higher for NO2. So for PM 2.5, we will not expect the results to change much, but definitely something to consider when we are looking at the estimation of the causal effect for NO2. But thank you, that's an excellent point.
So another clarifying question and an important one that just people need to know was about the data structure and what's used in the analysis from Jagadish Pugna. Basically to confirm, what is used in the statistical model, if the associations were evaluated at the individual level or at the zip code level. So
the answer is that they were evaluated at the zip code level. So we actually aggregate individual counts of mortality to the zip code level, and our models are fit at the zip code level. And the exposure is assigned at the zip code level, and then area level characteristics from census and are also, again, assigned at the zip code level. So the analysis is at the zip code level.
But to clarify, for the Cox proportional hazard model, the the association are estimated at individual level. It's just that, so we use individual level health data, but we have to assume that everyone within the same zip code has the same exposure. So in the zip code level and in the Cox proportional hazard model, the unit of analysis is the individual, but then as Danielle correctly pointed out, in the Poisson regression model and the causal inference model, we aggregate individual level data into age, gender, and strata counts. So then we do a Poisson model and achieve computational scalability. It's also important to notice that when we ran side by side the Cox model with the Poisson model, results were very, very similar. So the aggregation of counts within a zip code by age, gender, and race strata doesn't seem to change the results at all.
Thank you. We have a lot of additional time at the end of the presentations for more questions, both clarifying and otherwise. But we need to move on now at the moment, and we'll now have a presentations from Dr. Sarah Adar and Dr. Jennifer Peel. Dr. Peel will be presenting first, and then Dr. Adar will follow with her presentation. Dr. Peel is professor and section head of epidemiology in the Department of Environmental and Radiological Health Sciences at Colorado State University. She also holds an appointment at the Colorado School of Public Health. Dr. Peel is an environmental epidemiologist focused on evaluating the health effects of air pollution, both ambient air pollution in the U.S. and household air pollution from indoor cook stoves in lower and middle income countries. Her presentation will be followed by a presentation from Dr. Sarah Adar, who's Associate Chair, Associate Professor of Epidemiology at the University of Michigan School of Public Health. There has nearly 20 years of experience researching the health effects of air pollution, with growing interest in studying intervention strategies to reduce exposures and improve health. Both Dr. Adar and Dr. Peel are members of HEI's Review Committee and are also members of the Low Concentration Review Panel, which is before. Peel?
Thank you, Sveri. And I also want to take this opportunity to thank HEI for the opportunity to be part of the review panel working on this very interesting study, as well as to acknowledge on behalf of the committee that the committee found this report from these investigators to be incredibly valuable and obviously was an immense amount of work. This was a really ambitious, obviously, and a massive and sophisticated undertaking. And especially just thinking about the computational aspect of the study, I think it's important to acknowledge that very few groups in the world could undertake something along these lines. So incredibly impressive, and the committee really valued working with this study. Next slide. Thank you. And we will be focusing in this presentation on the highlights and especially thinking about what we are learning about the health effects at low levels of concentrations of air pollution. But I do think it's important to acknowledge what was already presented earlier by Francesca and Danielle, but it's worth noting the advance here and the key contribution in terms of the publicly available data for PM2.5 and NO2 and ozone predicted at the annual and daily average concentrations for the vast majority of the United States from 2000 to 2016. This is just a key contribution, beyond and complementary to the results that we'll be talking about later today. So also to point out that this is, incredibly valuable, not only for the availability of the prediction output, but also you can just see from the maps here that we saw earlier that these are valuable for the vast amount of the United States that these predictions are covering. So there are very few spaces in the United States that aren't covered by these prediction models, which has not been the case in the past. So this is an incredibly valuable advance. Next slide. So thinking about what we learned this study. One of the key takeaways is that we are seeing robust associations between PM2.5 and mortality in this population, and especially considering that these associations were including virtually all adults in the United States over the age of 65, which is incredibly impressive as we saw the sample size numbers. And importantly, including the rural areas with lower ambient and areas with lower ambient concentrations, which again was not always the case in the past. And this is filling a key gap in terms of our knowledge, being able to include these studies and have PM2.5 predictions in these rural areas with lower ambient concentrations. These associations, as we'll hear later from Sarah, were seen using 5 different statistical approaches, and really valuable to compare the results from these 5 different complementary approaches. And importantly, these results, when we look at the overall associations between PM2.5 and mortality, are really consistent with previous evidence that we have in the literature. So, utilizing these strengths in terms of approach and data availability, we are seeing some very consistent associations, and as well as filling in some gaps in terms of what we're able to utilize. Next slide. And as with any study, as we're thinking about these overall associations, and these are focused from these results, focusing on the results on the left, looking at the overall population, including all of the Medicare population. Of course, as with any study, there are potential limitations. As we were just hearing from the investigators, for many of these analyses, the exposure and the mortality data were used at the zip code level, and the hybrid nature of the covariates, where you had some individuals, some at the zip code level and some at the county level, could create some concern for residual confounding, as we heard. The committee did have a concern about the potential for and the validation where potentially no ground monitors exist, or very few ground monitors might exist. Especially at the rural areas with lower concentrations, this might be the case. Of course, this may not be a huge concern if the population, people don't live there. So this may be a lesser concern, but certainly something to consider. And importantly, this is, again, an incredibly large sample size, but it was only for adults over the age of 65. So we're not learning anything necessarily about mortality, PM2.5 and mortality in younger populations. Next slide. So another key takeaway could be that we are potentially seeing stronger associations at lower concentrations for PM2.5 specifically. And so here we would focus on the results for the low exposure cohort, which is the population where the PM2.5 was less than 12 micrograms per cubic meter. And those are the results on the right hand of the graphic. So we do see some stronger associations in this type of analysis for the low exposure cohort. This is consistent with some of the other recent publications and not with others. This hasn't been a consistent finding. And we do want to think about what could be driving these potentially stronger associations at this lower cohort. Our interpretation of that could be influenced by the different population that's included by a definition in the low exposure cohort. When we cut off the population to those experiencing PM2.5 less than 12 micrograms per cubic meter, we go from about 68 million in the Medicare population down to about 38 million. And necessarily, as you might imagine, those excluded might be different than those that are included in the low exposure cohort. So that might be influencing what we're seeing here, as well as some other potential reasons, including the different pollutant mix in those regions that are included versus those that aren't, and potentially some other explanations for what we're seeing there as well. Next slide. So a key contribution and a key strength of this study is the ability to estimate these exposure response curves that we saw earlier from Danielle, and importantly that they were able to estimate these exposure response curves across a range of pollutant concentrations, and including the focus of these studies, which was the lower ambient concentrations. In the past, many studies were able to estimate these exposure response curves with quite a bit of uncertainty when you got to the lower concentrations, and especially below the current standards. So here, as we've been talking about, quite a large sample size, even when you look at the population at the lower concentration. So quite a bit more certainty than previous studies to be able to estimate these exposure response curves. So as you can see, the curves are very similar. And here we're looking at the 3 pollutant model for PM2.5 on the left, adjusting for NO2 and ozone, and on the right, the single pollutant model for PM2.5. They're largely similar. There does seem to be some attenuation at the lower concentrations. It looks largely linear in the single pollutant model, whereas especially at the lower concentrations, there does seem to be some attenuation. It doesn't seem quite as strong at the lower ambient concentrations, and this isn't necessarily consistent with the previous results that we were looking at when we cut off the results were the population was cut off using only the low exposure cohort. So some caveats in terms of our interpretation for the low exposure. What's not uncertain here is that we are seeing this association that's quite robust and evident, whether you're looking at the single pollutant model or the 3 pollutant model, going down to a very low ambient concentration. Next slide. And here we see similar exposure response curves for NO2 as well, looking at the 3 pollutant model on the left, so now adjusting for PM2.5, and ozone, and on the right, the single pollutant model. And these are the same curves that we saw from Danielle earlier. So again, really important findings. Some key takeaways are the associations do look, or the curves do look fairly flat at the lower concentrations, and then you see a sharper upswing at the higher concentrations. Interestingly, though, the 3 pollutant model is showing these elevated associations. There is a different scale there for the 3 pollutant model, and those are all elevated in these results. So not necessarily consistent results for NO2 here, but certainly consistent over the range of the NO2 concentrations that were evaluated. Next slide. And again, here is a similar curve that we saw earlier from Danielle for ozone, with the 3 pollutant model on the left and the single pollutant model on the right. And here we're seeing these relatively flat exposure response curves at the lower concentrations, including, especially in the single pollutant model, some suggestion that the hazard ratios are below 1, which is, of course, we don't necessarily think that this is protective biologically, but it's something to perhaps investigate further in terms of what's going on. And I'll also note that this is not an isolated finding. We do see some similar findings in other studies as well, and including in the ELAP study that was also funded by HEI. Next slide. So in terms of summarizing what it is that we are learning in terms of the health effects at low levels of air pollution and what this work adds, again, there were some very key contributions in data and code sharing and advances in reproducibility that are complementary and equally important to the results that we're focusing on here in terms of the low levels of air pollution. There were numerous strengths that we've alluded to over the course of these presentations, and they certainly lend confidence in the results, and especially looking at the consistency across the statistical models that we'll go into further with Sarah in the next presentation. And thinking about the interpretation at the low concentrations, which is of course the focus of these studies, we do see this consistency of results for PM2.5 when we're restricting the population, and also looking at the shape of the exposure response curves. We do see these a suggestion of stronger associations, but certainly evidence that there are associations observed going down to a very low ambient concentration, including when we have adjustment for NO2 and ozone. On the other hand, the results for NO2 and especially for ozone, and particularly at lower concentrations of these pollutants, are not as clear in terms of what we're seeing at the lower concentrations. So with that, I will turn it over to Sarah, who will continue on with some comments from the review committee.
Great. Thank you so much. So I also just wanted to echo Dr. Peel's gratitude for being invited to join you today, and to have the opportunity really to evaluate this highly impressive study. I am going to be focusing on the causal inference approaches and what we can learn from these analyses. So just in the start of my talk, I'm going to spend just a couple very brief slides talking about the causal modeling kind of framework. I know it might be familiar to many of you, but I just wanted to make sure that we all recall what's been done, similar to what Dr. Dominici talked about earlier, and then just to help frame my comments. So when we think about causality, right, the core question we're really trying to get at here is, if we lowered air pollution levels, would we see improvements in life expectancies? And in a dream world, right, we'd all have time machines, and we could really look at the impacts of, a person being exposed versus that same person being unexposed in two different, alternate universes. But sadly, we all know we don't have time machines. And so we must use these other techniques to ensure that the people who we're comparing with exposure and with lower exposures are exchangeable or really fair comparative groups for each other. And so, Dr. Dominici talked a little bit about this, but traditionally observational epidemiology studies have used statistical adjustments to simultaneously balance lots of different characteristics at different levels of exposure. And now with more modern causal techniques, investigators such as the team at Harvard who did this really nice work are often trying to create these pseudo populations where, exposed and unexposed people are matched to each other based on their risk factors for the outcome. Or information from certain individuals can either be inflated or deflated in order really to make, the exposed and unexposed populations more comparable overall. Now, in principle, all of these techniques are designed to accomplish the same, thing. But traditional statistical adjustment often feels a little bit more black box, and it can be difficult to effectively see how balanced your populations are based on their exposure profiles. So I think, to me, this is really one of the places in which the causal models that were employed by the Harvard team really shines. And I know you've seen this graphic before, but I just want to really, kind of highlight how this creation of the pseudo populations with the matching and the weighting, the visibly checking of these characteristics, that may increase your risk of the outcome between exposed and unexposed, can be shown in these figures that are from the report. And in this full Medicare cohort, right, Dr. Dominici drew our attention to that green line, but I first want to actually draw your attention to the red line, which is the unadjusted cohort. So before they did any sort of, causal intervention, you can see these really clear differences between, exposed and unexposed group based on features of time. So that calendar year is the top one that shows high correlations between exposure and time, as well as place. And as we heard earlier, right, the methods that were employed to do the matching were highly effective. The weighting was also very effective in lowering those correlations between the exposure and these different covariates. And so that brings us again to this graphic, which we've seen a few times, but I think it's really important because it is showing across all of these different causal modeling approaches that were evaluated, the results are pretty much identical in the full Medicare cohort. And they're also highly consistent with the traditional approaches of the Cox and the Poisson model that we saw in the phase 1 report and some of the earlier papers from the group. So truthfully, this is probably not all that surprising to some of you, given that the models really are relying on the same data. But it's still very reassuring that different approaches for analyzing this data produce the same finding. I also want to say how grateful I am to the Harvard team for putting out this graphic, because it's a really nice contribution to the literature in that we very rarely see a comparison like this between sort of these modern causal approaches and the traditional approaches side by side in this way. So it's a really nice contribution that way. Now, adding the results that we see from the low exposure cohort, which again, you've seen a little bit earlier as well. What's noticeable here is that, there are some larger differences that we see between the modern causal approaches and the traditional epi approaches now in terms of the finding. It's still important to note that ultimately they're both reaching the same conclusion in terms of finding a positive association between PM mortality that's independent of other risk factors and appears to be larger in this low exposure cohort than the full cohort, the full Medicare cohort. So that raises the question of why might it be that there are these differences? And I actually saw that come across in one of the Q&A comments put in there. And I think that it comes back to this, point that I think both Dr. Dominici and Dr. Brown brought up about, one of the key features of these causal modeling approaches is that they are very flexible in their ability to adjust for confounding, and they don't impose these functional forms on the relationships with the confounders. And if you go into the report and pull out this lovely appendix table 2, it's very interesting because it really shows that this is likely the difference or the cause of the differences we see in the low exposure cohort. So what this is the team went and adjusted for covariates in the Poisson traditional model using more flexible functions, so using these penalized spline. And when they did that, they found that the approaches, again, for the traditional models, became much more step in step with the more modern causal approaches. So I think, number one, this highlights the fact that, the causal modeling approaches are very nice because they do this, flexible adjustment as a key feature, but it also affirms the effectiveness of more traditional approaches when you really carefully consider the adjustments for covariates. All right, so before I move on to more of the take-home messages and some of the strengths and limitations that the review panel was thinking through, I wanted to point out one other key benefit from this modern causal modeling approach that I found really helpful. And that's that these visualizations really help us to see in the, in that unadjusted cohort where you might have the most imbalance by exposure. So here for the low exposure cohort, it's interesting because we see that the confounders here differ slightly than in the full cohort. So most clearly, calendar year, which was the number one, place of imbalance in the full cohort, seems to be less important now when you're restricting to areas that are within compliance of the Knacks. But characteristics of place are now the ones that are coming up as having less balance in the crude data set. And so to me, that's valuable because it does help me to, really think about what might the primary sources of confounding be when doing these analyses. So that just leads to a few limitations and thinking about that. Honestly, these are very similar to what you've heard before. I would just start by saying, right, with all observational studies, our results are only as strong as the input data used. The great benefit of this cohort is that it's amazing, right? It is a massive cohort using the vast majority of the US population over age 65, again, with coverage across the entire United States based on the exposure models that they used. So from that standpoint, I think we worry a lot less about selection bias and who's making it into the cohort, but we are thinking still again about this exchangeability and the balance of confounders, by exposure level, which is why the causal modeling was so helpful. Nonetheless, right, we've already heard that you cannot create or check the balance on variables that are not in the data. So we're really restricted to things that are measured. We also, can really just ensure the balance of the data with the resolution that's being used. So here we heard again that, exposure and many of the covariates are on the zip code or sometimes county level. And finally, I just make a mention that, the specification of the variables when you're checking for balance and ensuring balance is also important. So thinking back to that issue of, area level confounding potentially in the low exposure cohort, region was adjusted for here, as was mentioned, which is great. But it was using 4 regions plus meteorology and other local characteristics. And so it's just something that we might be thinking about in terms of, whether or not there might be any residual confounding just due to that specification. In spite of, raising some of these potential uncertainties in the analyses, this work has so many strengths that are important to note, as we've heard a lot before. The large and comprehensive cohort with data for the entire United States is an incredible strength of this work. The causal modeling is also a great contribution in that it really is trying to mimic the randomized controlled trial. It also is providing this wonderful transparency of the covariate balance that I've talked about and others have talked about as being really valuable in understanding these associations. I think it was really, and the committee really found it incredibly important and valuable that there was consistency across these different approaches, both in terms of the model modern causal approaches, as well as more traditional models. And again, I think it really, needs to be said loud and clear what a wonderful resource has been created in terms of making the data available from the exposure perspective and the analytic code so that, these findings can be replicated and then reproduced across other settings, which again is something that we use in terms of determining causality. So with that, I'm just going to wrap up summarizing and reiterating some key points. I think, first we can say that the associations between PM and mortality across a range of different, modeling techniques deployed consistently showed, strong and positive associations. The transparency of looking at those covariate balances really increases our confidence in those findings. Although the panel did note some uncertainty remains due to measurement errors in the exposures and covariates at the zip code level and the potential for residual confounding. Of course, what's really nice is that we understand the investigators are continuing to do work in this area. We understand and heard that there's going to be additional control for other characteristics of place and the incorporation of measurement error corrections into the causal models. And finally, I just again conclude that this work provided really important demonstration of the consistency between these modern causal and traditional epidemiologic approaches that has implications not only for these findings, but also for air pollution epidemiology more broadly.
Thank you, Sarah and Francesca. We have designated time set aside for questions. And we have received a lot of questions in the Q&A space, so we'll kick that off right now. The first question has to do with the low exposure population, and there were at least a couple of questions related to that. The first by Katie Walker: couldn't the hypotheses that there's something different about the populations or pollutant mixes in areas with lower levels of air pollution be evaluated and resolved? And a related question from Yifan Wang: I think the study populations in the full cohort and the low exposure cohort are not the same, with different baseline hazards. And when comparing hazard ratios, is it possible that the higher hazard ratio is because the baseline hazard is lower?
Yeah, no, these are thank you. I think these are very excellent questions. And by the way, we have been taking note of all of the questions in the chat. There are many because they're always helping us to do better work. So with respect to whether or not there is a potential different composition of PM in lower and in area with the low PM and area with high PM, I think that's a great point. And I would say probably yes. And the good news is that as we are producing more work, more question, and this is something that it's a question that we can address. And so that's something that actually it's part of another piece of really important ongoing work that is coming from our lab in collaboration with colleagues that are more expert on the topic. So we will continue to work on this cohort, and it is our plan to look at the different composition in the low exposure area and the high exposure area, and the degree to which different composition might explain the difference between this estimated hazard rate in the low exposure area and the high exposure area. I think also there is a very important question, and I'm going to turn to Danielle, about potential systematic differences between the cohort that is always exposed at low level and the general cohort that is exposed both at low level and high level, which potentially results in different baseline hazard. And so, Danielle, do you want to say what we're currently doing and how we're going to, how we are planning to address it? Because this is actually really an interesting point.
Yeah, I agree. I think it's really interesting. I think one nice thing about these exposure response functions is that they allow us to look at the range of exposure, right, and fix one baseline across the entire cohort, right? So I think in one of the earlier slides, we defined the baseline rate as the estimated hazard rate corresponding to the exposure level equal to the first percentile of the distribution of that pollutant. And so the baseline is fixed. And so if you actually look at one of these curves, you can look at both the low exposure and the entire cohort kind of simultaneously. And it allows you to essentially look at the different slopes, right, and the effects and across like the range of the exposure. So I think that's a good point. I think that's one thing that these curves can be helpful at kind of putting on the same scale, both the entire cohort and the low exposure cohort. I hope that answered your question.
So there's a question from Andrew Lawson. With a focus on all-cause mortality, there must be potential mortality outcomes that are unrelated to pollutants. Does this not add extra noise to the outcome that could be avoided by a more focused study?
Yeah, that's also a very excellent point. So unfortunately, in the Medicare cohort, we only have date of death. We don't have cause of death. Other colleagues, even our former work, our previous work on the National Mortality, Morbidity, and Pollution Study, we used data from the National Center of Health Statistics, where we have cause of death. So can that add some noise? Potentially, yes. I would say that in this context, this is not something I would be mostly concerned because for two reasons. One is there is a lot of data. And two is I would expect the accidental deaths, although, there are important elements. I think the big chunk of mortality or cause of mortality among 65 years old is cardiovascular and respiratory. But nevertheless, to say, I think that there is a lot of advantage of looking at cause-specific mortality. And in fact, our colleagues, Bert Brunekreef and Michael Brower, their own study are looking at cause-specific mortality, which is definitely a plus, a great strength of their study that we don't have.
Thank you. A question from Carl Brown on temporal trends. Did you adjust for or account for the temporal trend in air pollution at all? Figures showing air pollution levels in 2000 and 2016 seem to show a decline in each pollutant over time.
Danielle, do you want to take that?
Sure. So first of all, the mortality in a given year is that we assign an exposure to it. That's the exposure in that year. So in that sense, a kind of the pollution is assigned to match the year of the mortality. And we do include also year into the model as a sensitivity analysis. And we saw that the results are robust to that inclusion. So yes.
So there's a question about there are a couple of questions about NO2, and it says from it seems to me likely that NO2 is a surrogate for local traffic related PM, such as black carbon and ultrafine particles, or do you think that NO2 is biologically plausible causal agent for cardiovascular outcomes? And another person asked, how do you interpret the NO2 results? So I think some more explanation on NO2.
Well, I mean, it's we don't have, first of all, let me make clear, we don't have all of the answer. So I think it's well known that NO2 tends to be a surrogate for traffic exposure. And I think that they're being consistent, and a lot of additional studies are looking and have been showing evidence of an association between NO2 and cardiovascular disease. So I think, in terms of the biological plausibility, I will defer to additional study where they have provided the toxicological evidence that traffic-related pollutants are biologically plausible to provide adverse health effect in the cardiovascular system. But this particular study, I don't think can illuminate in terms of biological link, biological plausibility.
Thank you. A question from an anonymous questioner about I think lags and the relationship, temporal relationship between the exposure and the outcome. So, is the data on how long the exposure needs to be before the effects start to be noticed?
Well, that's another great question. So this is something that we could explore more, and we have not. What we have done in the study is have, for every individual, we calculate as long-term exposure, the exposure that he or she had in the previous year. In the past, we have done sensitivity analysis to see whether estimating the exposure of a longer time period make difference. By longer, I mean 3 years. Or 5 years, I believe. We didn't see it, the big change. However, I think now that we are now a cohort that goes from 2000 to 2018 because we're buying additional Medicare data. So I could see that actually this is a phenomenal additional investigation where we have the ability to estimate how long you have to be exposed to a certain level of PM to then see an addition, to see an increased risk. So I'm grateful to the person that provided the question, because I think that would be an additional study that I think would be very worthwhile to do.
Okay, we have a question from Benedict Armstrong. Are GPS methods robust to confounding by covariates with profoundly nonlinear associations with outcome?
Yeah, and that's one great advantage, I think, of the GPS matching is that It allows you don't need to include these covariates in your outcome model, right? So especially nonlinear covariates, if you did assume that they were linear in the outcome model, that would lead to huge model misspecification. And one advantage of including them in the generalized propensity score is that you don't have this model misspecification in the outcome model anymore. So yes, the GPS models are more robust to model misspecification in that sense.
Thank you. Question regarding the exposure model from Binjo. Could the high R squared that's achieved by the exposure model be ascribed to the seasonality inherent in the data, given that ambient temperature of several of the pollutants like ozone and are temperature dependent?
So we will need to have Joel here to really properly address the question. My understanding, and that's why it's my understanding, because I don't want to misspoken for the work he has been leading, is that there is a seasonality element into the prediction. These are very complex and very rich non-parametric model. This is a deep neural network. So I'm confident, but not certain, that there was a seasonality element into the model. But we will definitely take a note and make sure that if it's not, we will be looking at that issue.
We have a question from Jagadish Puvula. Could you also confirm the data structure being used in the statistical model? If the associations were evaluated at individual level, assuming study participants in the 1 kilometer grid exposed to the same pollutant concentrations, or at the zip code level?
So to clarify, in the Medicare data, when we buy the claims, the claim is individual, right? So we know the individual age, we know when, the date of that, but we only know the place of residence based on their zip code. We don't know the residential address. That's how the bill is constructed. So when we fit the survival model, we look, our data set, how it's linked across data sources, that we preserve in the Cox proportionalizer model, the individuality of the record. So we account and consider individual level age and individual level gender. But then when we assign the exposure, because we don't have the residential address, we only have the zip code, we needed, what we do, we take the 1 kilometer to 1 kilometer grid exposure and we aggregate it up to the zip code level exposure. So in other words, everyone in Medicare, everyone who lives in the same zip code will have the same zip code. We'll have the same exposure. We don't account for the fact that people within a different zip code, we don't account for people that might have a different residential address within a zip code that might have a different exposure. If that's the case, that's something that in this initial analysis, we didn't account for it. But as Danielle has pointed out, there are 2 additional work in progress from which we are accounting, because we don't know how much the exposure to PM2.5 vary within a zip code, right? And so we are now propagating the uncertainty into the health effect analysis. And there are a couple of publications that are under review right now, and hopefully we will be able to report on the issue soon. Danielle, is there something you want to add on that issue? Because you're really the mastermind around this.
I think that covers that.
A question on the value of the Poisson analyses from Liu Hua. Sure. Well, since the stratified Poisson is Cox equivalent, according to other publications, what's the point that you fit both the Cox model and the Cox equivalent Poisson model?
Yeah, so we've shown in derivations that it's equivalent, but it was really important for us to assess in terms of implementation and our software to make sure that it was indeed equivalent. So that was the reason that we actually fit it. And I think it increases the robustness of all of our findings to even 2 models that are equivalent, to implement them in 2 different ways, I think is important. So.
Thank you. There's a question from Michael Clegg. Given the number of covariates in the GPS, how can you be sure that you are not overmatching and thus underestimating risk?
Yes, it's a good question. I think it's also a bit tricky to think about what overmatching would be in this context. I think one thing to emphasize is that this framework does allow us to evaluate kind of the robustness of how well we created the pseudo population using the absolute correlations. And so again, using all the covariates, if you have many covariates, in our case, we had 14 covariates, you can actually evaluate the correlation for each one of them. Maybe if there is time, they can follow up with a clarification on what they mean on overmatching, but I think essentially that absolute correlation allows us to kind of assess the quality of our pseudo population and move on with our outcome analysis based on that population.
Thank you. A question from Perry Heistad about the multi-pollutant models. It appeared that you include NO2 and ozone in the GPS model as well as separate covariates in the same health model. He's not sure about that, but I guess that is a clarification question. Does this suggest that the GPS didn't fully capture the correlation structure between pollutants? And did you test this for other covariates? I guess rather than testing NO2 and ozone rather than just the PM correlation.
So thanks for this clarification. So we in fact only include them in the generalized propensity score model, not in the outcome analysis. And we did evaluate the absolute correlation, although we didn't show the results, but we did evaluate that absolute correlation after we do the GPS matching. And we do show that for NO2 and ozone, we are able to achieve good covariate balance.
Good, thank you.
There's a question from Chad Bailey. Could you please talk about the steps you use to process satellite data and for use in the exposure model?
Well, we are not in a position to give you exactly detail because, as I said, that's something that our colleague George Wurst led. But I think that if you look at their publication, they should be able to give you all of the details. My understanding is that they download from NASA gridded daily level of aerosol optical depth. And so that was one of the input that went into the machine learning model, in addition to output of additional atmospheric chemistry model. But the output of it is publicly available, and you can definitely, I will refer to the publication to really look at all the different steps.
And I just want to mention that in addition to the 3 publications that we included in the slides for each of the pollutant models, we do have a publication that's on AirPred, which is a software package that we put together to help facilitate some of this. So I think that would help answer some of the questions on the details as well.
Thank you, Danielle.
Going back to the topic of the difference between the low exposure population and the general total population. A question from Archana Lamachan. Can you comment a little bit more on the difference in estimates obtained from regular regression models versus causal inference approaches when the analysis was restricted to the low concentration population? What may be going on here as compared to the unrestricted analysis when no difference was observed? Does this have anything to do with the difficulty in matching when you go to the low exposure, hence more uncertainty contributing to the differences observed?
So I'll get started, and I'm sure Danielle will have many additional insights. So I think that what the question is referring to the panel on our right side. So that panel shows the estimates of the hazard ratio for 10 units increase in PM 2.5 exclusively for the low exposure cohort. So, and you can see from that panel that we have the Cox and Poisson. So we have the estimates of the hazard ratio under the Cox model and Poisson, and they're very similar. The Poisson, it's a little lower. And then we have the three estimates under matching using exact matching by the propensity score, weighting by the propensity score, and including the propensity score as a covariate. And so clearly there is difference where the estimates from the models from the causal inference approaches tend to be lower with respect to the one that are under the traditional approaches. And we see more of a difference between the traditional regression and the causal inference under the cohort that is posed level below 12, whether we don't see much differences when we look at the full cohort. And so I think that one explanation here is that when we are analyzing the data exclusively for the people that are exposed at level below 12, the standard way of adjusting for confounding, so by including all of the potential confounders as a linear term, might be less adequate. And so the causal inference approaches, because have this advantage of adjusting for confounding using the generalized propensity score. And so basically having one unique score to potentially account for no linearity in the confounders, that's actually where we see that's they we're likely to provide the less biased estimates. We are confident that the estimates from the causal inference model under the low exposure cohort are getting closer to provide an evidence of causality and adjusting for measured confounders, because again, as Sarah pointed out, and as we show, when you look at the plots of covariance balance, we are achieving covariance balance. So if you look at these green dots and the blue dots in your right side of the panel. And so I think that the bottom line is in the low exposure cohort, we believe that if we would have to use only the traditional regression, we would be relying more strongly on parametric assumption, and therefore we could have led to an overestimate of the effect. Danielle, is anything else you would like to add?
No, I think that summarizes that. I think it's most likely due to model misspecification being more present in the low, in the cohort that was exposed to low PM 2.5. I think it's very reassuring that we're able to achieve covariate balance after matching and weighting. And so I think that kind of, again, ties in with these results and the reassurance. And one advantage of the causal inference methods is that we do have this kind of reassurance about these estimates here on the right.
Thanks. Another question, the one from Philip Blagden. Can you elaborate on the calculation of the 143,000 avoided mortalities over 10 years if the PM 2.5 Knacks were to be reduced 10 micrograms per meter cubed? How did you adjust exposure across the population?
How do we adjust exposure across population?
I think the point is, can you elaborate more on that calculation of the avoided deaths, the 143,000, the avoided mortalities over 10 years?
Danielle, do you?
Yeah, I mean, I can say that we use the hazard ratios that we estimate to do this calculation of how many lives we would save if we lowered to 10 micrograms per meter cube. I hope that answers their question, but it's based on the hazard ratios.
So there is, if you see, there is a link to the publication, and if they link to the method section, it's clearly defined of how the number was obtained, as well as the publication will lead you to the code, the R code, so you can see what were the assumption and how, and you can actually reproduce that number.
There were a couple of questions related to indoor air exposures, and I'll just present the one from Michael Young. Does your model account for indoor air quality exposure where, for example, solid fuel stove users may have higher levels of indoor air PM and a range of more toxic components?
No, there is no, all of this analysis is strictly to ambient exposure.
I guess that raises the question whether the indoor air could somehow influence the effect estimates, if potentially it's related to ambient PM.
Yeah, I don't know. I think you know, we will need to have a systematic high indoor air in a way that is uncorrelated with outdoor air to really confound or revert the results of this study. I will really refer to the large body of the literature, and there are excellent studies out there that are really designed to look at this issue. This is not the issue that we were being focusing in this study.
So it looks like we've reached the end of our time. I know there are a lot of other questions, but I want to thank everyone, my co-hosts, Danielle, Francesca, for excellent presentations, Sarah and Jennifer from the review panel, Dan as well, other HEI contributor here. And I want to thank all of our participants today for joining us for this webinar. The recording for this webinar will be posted on our website, and please visit our website where you can freely download this report and a copy of the commentary from the peer review panel. And for that, I want to thank everyone, and I wish everyone a rest of the good day.